So in this lecture, we'll look at P, NP, and NP completeness and give an introduction to these concepts in an informal way. The next two parts would define P and NP more precisely and NP completeness more precisely and look at examples of NP complete problems. So this is again a guest lecture I'm giving in MEC. We will also lead today to this this famous question as to whether P is equal to NP or not, which is one of the most celebrated open problems in computer science and even in mathematics. It's a very long-standing open problem, and a lot of attempts have been made to settle this, but it's not been successful so far. There are even $1 million prizes for the person who proves this. So we'll tell you what this problem is in this lecture. So most of the problems that you've seen in this course have had polynomial time solutions, like searching, sorting, finding minimum spanning trees, shortest paths. They've all had solutions that are order n to the k, where k is a constant. So these are in general algorithms that work quite fast in practice, especially if k is small, and these are called polynomial time solvable problems. So let's generalize this and define this class called P, which is the class of all problems that can be solved in polynomial time. So P is the class of all problems that can be solved by some algorithm that takes polynomial time. Now, one could of course ask the question as to whether there are problems that cannot be solved in polynomial time. And of course, if you've taken a theory of computation course, you know that there are problems that are not even solvable, that these are called undecidable problems, for which there are no algorithms at all, let alone polynomial time algorithms. For example, if I gave you a program P and I asked you an assertion in it, and I asked you whether the assertion is always valid, that turns out to be equivalent to Turing machine halting problem, and that's undecidable. There is no algorithm for it. So obviously there are problems which cannot be solved in polynomial time. But now let's look at the class of problems that are decidable. So even here you could ask, is every problem that is solvable in polynomial time? And the answer again is no. There are problems that require more than polynomial time. For example, if you know the theory of computation course, then if I give you a context-free language and I asked you whether it's contained in a regular language, it turns out that this is decidable. You can complement the regular language, take the intersection with the CFL, and check the CFL for emptiness. So it is decidable, but you can show that there is no polynomial time algorithm for this problem. So so there are algorithms that will take much longer than polynomial time. Now there is another class of problems that have solutions in this class called NP, which turns out to be very interesting. So NP is the class of problems that can be solved by algorithms that are non-deterministic and work in polynomial time. So NP is the class of all problems that can be solved by some non-deterministic algorithm as opposed to a deterministic algorithm for P in polynomial time. Right? And what is a non-deterministic algorithm? It is a very strange, unintuitive notion. So if you know non-deterministic automata, NFAs, they're similar to NFAs. So in your favorite programming language, you know, let's say it's an imperative programming language where you could write something like if x is less than phi, then do something, else do something. In a non-deterministic algorithm, you can do something like a guess. You could say if star, then do this, else do something else. So this is a non-deterministic choice which says that the program can go into the if branch or the else branch non-deterministically. It can choose arbitrarily which how this star is going to evaluate. If it evaluates to true, it will go into the if branch. If it evaluates to false, it will go to the else branch. So now, natural programming languages are not non-deterministic. They're not at least meant to be non-deterministic, and so this notion of a non-deterministic algorithm is very strange. And the reason why non-determinism is interesting is that suppose in order to solve a problem, there is this very large search space, right? An exponentially large search space on which I have to find whether one of these points is suitable in order to solve the problem. Right? A deterministic algorithm will have to spend exponential time intuitively to look at every one of these points to check if it's a solution. Whereas a non-deterministic algorithm can magically pick up the right solution if there is one. Right? So we'll come back to this definition of non-deterministic algorithms, but essentially they look like they are very powerful. They're not physically realizable. We can't realize them using a computer or physics, but what it allows us to do is solve problems much faster than deterministic ways of solving them. So going back, we have this two classes, P and NP. NP is the class of problems solvable in polynomial time, but using non-determinism. The interesting question is whether these two are the same, right? Are all NP problems solvable in P? The reason why this is interesting is that people have found hundreds, even thousands of problems that are solvable easily in NP, that they have a non-deterministic polynomial time algorithm, but people don't know whether there is a deterministic polynomial time algorithm for that. Okay, so there are these large class of very interesting problems from various domains of engineering, mathematics, anywhere you take, right? And all these problems have non-deterministic algorithms that work in polynomial time, but no one knows whether there are deterministic algorithms for them or not. Okay, so the P is equal to NP or not question asks whether every problem in NP can it be solved in polynomial time. Now note, of course, that P is a subset of NP. But the question is, if I have a non-deterministic algorithm that works in polynomial time, does it mean that there is always a deterministic algorithm that works in polynomial time, solving the same problem? Now, most researchers believe that P is not equal to NP, that none of these hard problems which we want to solve in polynomial time are not solvable in P. That's what most people believe, but the exasperating fact is that we have not been able to prove this. We have not been able to show that these problems do not have polynomial time solutions. Now there is a lot of study in this area, but it turns out that there is a subclass of NP problems, right, which are called NP complete problems, which are in some sense the hardest problems of NP, right? So think of NP complete as the hardest problems in NP. So these are the hardest problems that have a non-deterministic algorithm that works in polynomial time, right? The notion of why it is the hardest we'll define later. But it turns out that if you can solve one of these NP complete problems, any one you can pick, if you can solve that in polynomial time, then you can show that the entire class of NP can be solved in polynomial time. So that's why they are the hardest problems. If you solve one of them in polynomial time, in deterministic polynomial time, then you would have solved the entire class NP, will collapse to polynomial time. So, so if A is NP complete, then A belongs to P, polynomial time, if and only if P is equal to NP. So if you prove an NP complete problem is in polynomial time, then the two classes will collapse. And moreover, if you show that any NP complete problem is not in polynomial time, is not solvable in polynomial time, then you can prove, of course, that P is different from NP. Now, it turns out that NP complete problems themselves form a very interesting class. So people have discovered hundreds of problems that are NP complete. So they're very hard to solve. You can provably show that they are the hardest problems in NP. Right, and these come from, again, from a variety of domains, including all facets of engineering, combinatorics, etc. So you could ask, this is all fine in theory, why should I know this as a practical computer scientist working in the industry, right? So in practice, it is important to know about NP completeness, because if when you are given a problem A that you're trying to solve fast, if you find a polynomial time algorithm, then you could of course try to improve it and make it work fast. But if suppose you cannot find a polynomial time algorithm, right, then you could try and argue that A is actually NP complete, right? Now, if A is NP complete, if you can prove that A is NP complete, then you know that it's very unlikely that you're going to find a polynomial time algorithm, and you could go and argue to your boss saying that this problem cannot be solved in polynomial time by you, but that it's above your pay grade, no matter what your pay is, because no one in the world knows how to solve this problem in polynomial time. Right. So if A is NP complete, then solving A fast, that which is means in polynomial time, is unlikely. Right. So this allows you to recognize hard problems in practice, and again, as I said, it is not uncommon to find hard problems in practice. Many combinatorial problems, search problems, are actually NP complete, and so recognizing these problems as NP complete problems will enable you to look for heuristic solutions instead of solutions that always work. So in the next lectures, we will look at a more formal definition of P, NP, and NP completeness, and look at examples of NP complete problems.